If there isn't sufficient energy, the collisions won't be able to break the intramolecular bonds, and the reaction won't proceed. Increasing the energy input gives the reactants the required energy to reach the transition state upon collision, where intramolecular bonds of the reactants are broken and new bonds are formed. In reality, relying on activation energy input alone can be impractical. A catalyst is a substance that speeds up a reaction without being consumed. A catalyst provides an alternative pathway for the reaction having a lower activation energy requirement. There are different types of catalysts, which employ different mechanisms accordingly. A catalyst interacts with reactants in a way that breaks their intramolecular bonds to form either temporary bonds or intermediaries, enhancing their reactivity. These temporary bonds between catalyst and reactants are weaker than the original reactant's intramolecular bonds, making it easier to break them upon collision with other reactants. A catalyst can also hold reactants in the optimal orientation and in close proximity to each other, increasing the overlap between their electron clouds, encouraging bond formation. This is an example of a solid nickel catalyst used in the production of ethane from ethylene and hydrogen. The hydrogen has an affinity for the catalyst, so it's drawn to it. The close proximity of the hydrogen to the catalyst causes the hydrogen molecule to adsorb on the catalyst surface, breaking the bond between the two hydrogen molecules. Temporary bonds are formed between the hydrogen atoms and the nickel catalyst. At the same time, ethylene has an affinity for the catalyst and similarly adsorbs on the surface, resulting in carbon double bond breaking to accommodate the carbon-nickel bonds. The adsorbed reactants move along the catalyst surface until they collide with each other, forming ethane as a product. Ethane desorbs from the catalyst.